Hello, everyone. In this video, I'm going to present an innovative approach to remote attestation with a special focus on two key moments in the application lifecycle: the demutra mechanism, which handles attestation before the program starts, and our proof of concept that demonstrates attestation during execution. This video showcases a front-end interface we developed to visualize and interact with these two stages of attestation in real time. In D6G, mess agents are configured and deployed as containers by the MLFO. With a single line of bash, we interact with the agent creation workflow to append a sidecar to each agent, acting as both prover and verifier. Sidecars measure their agent and themselves, and verify measurements received from peers. Hence, remote attestations are produced through mutual interactions between sidecars. At the same time, the TSS plays a crucial role by generating reference measurements for each agent before deployment and later acting as a verifier or a provider of reference data for peer-based attestation. Finally, the DLT handles the election of verifiers and maintains a record of which agent was attested and by whom. During the reference measurement generation phase, the MLFO first retrieves the code file of each agent. It then sends these files to the TSS, which parses each one and produces a reference measurement that is stored in a database. Finally, the TSS generates and returns a unique identifier for each agent to the MLFO, which will be used to identify them within the DLT. The final step before starting the attestation of the agents is to link each sidecar with its corresponding agent by providing the metadata file, which includes the generated ID. After this, all agents are ready to be attested before they can start. Let's begin the attestation with Agent 1. First, the MLFO initiates the attestation by sending a request to Sidecar Container 1. The sidecar starts the agent to access its process memory and immediately suspends its execution. The agent will only be allowed to continue if the attestation result is positive. From there, the sidecar reads the process memory and generates a fresh measurement of the agent. It can then send an attestation request to the DLT, including the newly produced measurement. The DLT retrieves the ID and the measurement from the request and can now record the attestation request for Agent 1. It must then decide who will act as the verifier for this agent. Since this is the first agent to be attested, the TSS will be designated as the verifier. The DLT then sends a request to the TSS, assigning it as the verifier, along with the metadata in the fresh measurement. With this information, the TSS is able to compare the fresh measurement with the reference measurement and determine whether the agent's integrity can be attested. Next, the TSS sends the result back to the DLT, which creates a transaction recording the attestation outcome. Finally, an event is sent to Sidecar Container 1, which will decide whether to allow the agent's process to continue based on the attestation result. Now we want to attest the second agent. The beginning of the workflow remains the same as with the attestation of the first agent, up until the point where the DLT selects a verifier. As Agent 1 has recently been a tested entity, it can be used as a trustworthy verifier, hence entering the chain of trust for verification. This chained verification by agents themselves prevents DOS attacks targeting unique verifier, as would be the TSS. So the DLT will select the agent's sidecar as the verifier and send it the request to verify Agent 2. The additional step compared to the attestation of the first agent, the verifier must first retrieve the reference measurement from the TSS, then compare it with the fresh measurement it received in order to perform the attestation. Finally, the last step is the same as for Agent 1's attestation. Sidecar 1 sends the result to the DLT, which creates a transaction recording the outcome. An event is then sent to Sidecar 2, which decides whether to resume the agent's execution based on the result. Let's now look at an example using our front-end setup. 2 MAS agents containers from UPC, 2 sidecar containers, 1 per agent, 1 SE-CAS instance, for reference measurement generation and verification, 4-node Ethereum DLT network for managing attestation records and verifier selection. This Docker stack allows us to simulate the full demutra workflow with mutual attestation, verifier election, and blockchain-based integrity validation. First, we will generate the reference measurements, which will also produce unique identifiers for each agent. Next, we can begin attesting Agent 1. As soon as we send the attestation request, the remote attestation mechanism with our blockchain is triggered. Now we can see the measurement time results, which are very short, around 1 to 2 milliseconds. This is expected as it involves a simple memory read followed by a hash computation. The verification time is longer than the measurement time because it includes both a database request to retrieve the reference measurement and the comparison of the hashes. Finally, the full attestation time includes network requests and the round trips between the sidecars and the CICAS. Let's now talk about the key features of our remote attestation method. Blockchain-based distributed remote attestation, no single point of failure attack, immutable stores on the blockchain, distributed resource consumption over the peers. Platform-agnostic, not dependent on TPM, kernel module, or attestation framework. Zero-touch management for signatures, CSS stores, automatic signature updating, and timely provisioning at the elected verifier. An ultra-lightweight component suite with effortless, containerized deployment. Just run a script or use Docker Compose for full control. Now let's highlight the key points that make our method an innovative remote attestation approach. Verifier election based on integrity freshness, higher security criteria versus SOA, random round robin or random selection, probabilistic approaches. True mutual attestation, agents prove themselves and verify their peers without third parties and certification authorities. Right. Demutra merits are great, as relaxing a lot of constraints for applying remote attestation. This being said, remote attestation when operated before running the code induces a severe latency, retarding the execution of my code. How can this issue be solved? That is exactly what this PoC is all about. Penalty killer. For that, it develops runtime integrity verification, which delivers two key benefits of attest after starting and continuous attestation attest after starting. Simply cancel any latency at payload start. Let us dig how continuous attestation is done and how the performance penalty is adjusted. Before that, let us recall what is measured. What element does the runtime integrity attestation rely on? Our runtime integrity verification focuses on the .text section of the process, specifically targeting ELF-formatted x86 executables or libraries. We compare the .text section from the original binary file with the corresponding load segment in memory, which contains the same code section. This allows us to detect any unauthorized modifications made during execution. We are here digging how to install the blockchain and how to set up the service. What am I supposed to do with a blockchain? Where should it be installed? DLT nodes are not necessarily the execution platforms for your payloads. They can be deployed wherever sufficient resources are available, with two main criteria in mind. Relative proximity to the payload. The sidecar should connect to a nearby DLT node to ensure acceptable communication latency. Sufficient number of nodes. Increasing the number of DLT nodes enhances the security and resilience of the DMU-TRA system. Let us consider a setup of the blockchain in Desire 6G architecture mass. Agents are located in the different core technical domains of radio, core, and cloud. As previously mentioned, DLT nodes can be deployed locally within the physical infrastructure, provided that sufficient resources are available. However, if the local environment lacks the necessary capacity, these nodes can just as easily be instantiated elsewhere. What are the software requirements for Demutra to be operated? You have two options. Either manually run a script to launch the sidecar containers and the SECAS as needed, or integrate the sidecars into the Docker stack by modifying the Docker Compose.yml file. Now let's look at the proof of concept for a test during running. This method enables continuous attestation of any agent in any order, thanks to the sidecar measurer. Let's now explain why it's important to perform continuous on-the-fly measurements. Let's take an example with 3 measurements taken at regular intervals. Between 2 measurements, there exists what we call an attack window. It is a period during which an attacker could compromise the system by altering the measured state and then restoring it before the next measurement. As a result, the attestation process fails to detect the compromise because it only observes the system at discrete points in time and not what happens in between. The advantage of having a low continuous remote attestation frequency at runtime is that it results in minimal CPU usage. This makes the approach lightweight and suitable for resource-constrained environments, while still maintaining a basic level of runtime integrity monitoring. To explain the performance impact, let's imagine our program as a car, and remote attestation is like a speed bump. The fewer speed bumps there are, the faster the car can move forward. Similarly, the fewer attestations performed during runtime, the less the system is interrupted, resulting in better performance. Now, by increasing the measurement frequency, we reduce the attack window and increase the likelihood of detecting a compromise. This is because the attacker has less time to modify the system and restore it to its original state before the next measurement takes place. In other words, the shorter the interval, the harder it becomes to perform undetected tampering. The number of taken measures to build one block is adjustable and linked to the acceptable blockchain inflation rate. As one agent attestation footprint is 600 bytes, taken 3 different agents verified every 2 seconds generate an inflation of 28 gigabytes per year. 2 methods are considered to control the inflation rate. Aggregate several measures for one block creation or generate transactions only for tampering detection integrity failure. By default, the measurer runs an infinite loop of measurements at the maximum capacity of the system it operates on, resulting in a high number of measurements per second. If this CPU load is too demanding for the system, it can be adjusted using Linux's C Group v2 feature to control the CPU usage of the sidecar measure. As soon as we lower the CPU limit, the number of measurements decreases. Let's look at an example with our front end. Here the agent is already running, and we are now starting the attestation process. Right away, we can see the number of measurements, the measurement rate, in measurements per second, the number of verifications, and the number of attestations being displayed. We also see the CPU usage of the sidecar measure, which we will adjust shortly. Additionally, we can observe the duration of one of the tasks continuously performed by the running agent. Now we're going to adjust the C group settings and relax the CPU limit from 10% to 90% for the sidecar measure. We'll observe the impact not only on CPU usage, but also on the frequency of measurements, which is expected to increase significantly with more available resources. Instantly, the number of measurements increased from 20 per second to 200 per second. We observe that the agent's task duration has significantly increased, rising from 4,000 milliseconds to over 7,800, nearly doubling the execution time. Of course, this duration may vary depending on the specific characteristics of the system. Here's a summary of the key takeaways from our proof of concept. 0 latency at payload start. Agents start instantly. Attestation runs in parallel with no startup delay. Text section measurement. We verify runtime integrity by comparing the .text section of the binary with its in-memory counterpart. Security versus performance trade-off. Users can tune measurement frequency to balance CPU usage and detection accuracy. Blockchain inflation rate trade-off. Aggregation frequency controls the volume of data stored and the freshness of tampering alerts. Thanks for your attention.